All right, so let's. All right, so let's start. So hello everyone. This is Hao, and I'm working with Vsoft, and Vsoft is our company is a startup, and our product is called Nebula Graph, which is a highly distributed and highly scalable graph database. And I believe our first presenter, Wei, will have more introduction on Nebula Graph. And during today's meetup, we will mainly have three topics. And first, we will have Wei from Vsoft to talk about the new features in Nebula Graph new release, which is version 2.5.0. And after that, we are very happy to invite our customer from Akulaku to share their experience of using Nebula Graph. And finally, we will have someone from Facebook to share the experience of RocksDB. And we will, after that, we will have some time for question and answers. Okay, I will then hand over the access to Wei.
Thank you, Wenhao. So I will share my screen. Can you see it?
Yes, I can see your screen.
Okay, thank you. So thank you, everyone. Good afternoon and good morning. So this is Wei Gu from Vsoft, and I'm wearing the hat of developer advocate. So in future, for anything you consider needing help, just reach out to me from the Slack, the forum, or Twitter. I will start the first part to introduce the what's new in the core Nebula Graph of 2.5 and something also in the surrounding tools. We will start with the repos. As we already know that since the version 2, we have switched from the mono repo structure to the sub-modules. So in 2.5, we have 3 repositories for Nebula Graph core. And you can check the race node from the documentation website, and you will see the features, the enhanced features, and all the PRs link will end up being referred to all of the three repositories. So they are the graph for the query engine, the storage for the storage engine, and the common part. And in this release, we have mainly 3 parts of the new contents: the scalability and the new features, and some existing function enhancements. So we will start with the scalability, which is actually the main focus in this release cycle. The first one is that we now introduce a mechanism of the memory watermark. So it's configurable, named system memory high watermark ratio. And after you configure this value from the query engine, the GraphD, this mechanism was targeted to reduce the possibility of the OOM when a large amount of RAM is consumed during the query. but there are some, so it's actually kind of partially implemented. So for now, the current implementation is not, doesn't fit the case when the graph D is running in the environment of container. So in this release, if you are running Nebula inside Docker or Kubernetes, it's better to turn this feature off by setting this to 1.0. And there are some other issues in this feature. For example, it cannot calculate the initialized memory when it's actually cached. So, and that's all about this one. And the next one is we optimize the heartbeat implementation of Raft. So it's not impacting our user face. And there are some other small scalability improvements which we didn't highlight here. And also for the common issues, you may refer to the documentation. There is also a PDF edition of this doc. There is a FNQ section. You can refer to that first in case some issue happen. And then we come to the new features. The first one is the slow query termination. That in 2.5, we introduced a new function to enable user to query the running long run queries. And if you change your mind, you would like to kill it, it's possible. Just like this, you can kill the query based on session and plan ID. But for now, it's only implemented on the query engine side. That says you only kill this process in the graph D rather than all the running processes on the storage D, but it will be implemented in the future cycles. The next one is finding path. Now we can finally support filtering the edge properties during a find path query. So as you can see here in the where clause, we can filter based on the edge properties conditions here. But still we cannot support the vertex properties filtering. So you can if you would like that to be supported, just stay tuned. We will support in the future releases. Next one is the subgraph. For now, previously, our subgraph will fetch everything, including the edges, the vertexes, and all the properties by default without options to disable. So now we bring this option to the user. So with the new parameter during the subgraph query, you can specify. You have to specify on prop. It literally means you would like to fetch all the properties, but without this specification, only the topology of the graph will be fetched. That is only the vertex and edges. So this is actually a behavior change. We will review that later. Another one is now it's possible from the in the service level, you can query the binary versions inside the NGQL. So like this, if you show host graph, you will see all the graph instances with the gate and the version infer. So inside the query. So the last one is a minor one, and when you create a space, you can now it's supported to specify the comments fields. So it's very sweet small feature. And that's all of the new features. And regarding the enhancements, the first one is now previously we cannot use, for some reasons, we cannot use the index together with the TTL, and now they can coexist. So there are some minor limitations. Please refer to documentation. There is caution on this chapter. So the next one is regarding the full text index. So now the full text index can be applied to specific properties rather than all of them. And also it can now finally support the rebuild. And next one is that we introduced a mechanism called disk manager to prevent the system from being damaged and the data being damaged due to the situation of this disk full. So we introduced a variable configuration in the storage D, and by default is in 1 gigabytes. And when this threshold will be exceeded, the system will prevent some of the operations to stop, to prevent it from the data from being damaged when disk is actually full. The next one is small one. That now the function exists will support checking one of the key of a map map instance. Like you can in your match query, you can now check whether key A exists on this variable. The last one is the aggregation function. Previously, when you query something like return the aggregation of the count of V plus the average of V, so it should be supported, but previously it will end up with the error of we don't support nested aggregation. We know it's not nested, so now it's fixed. So there are some other enhancements that's not impacting our user space, but it's somehow optimal. The first one is now the storage engine supports the execution of the query in a concurrent way. The background of this change is that previously in the legacy version, we actually we have a period that support this kind of execution, that you don't run your query in single process. But it turned out we thought and we observed that it's not performant in the OLTP situation. So when you have high concurrency, the single process performs better. So we disable that. But in this release, we optionally introduced the possibility to user. By default, it's configured disabled, but you can enable it. So in some cases that it's not in high concurrency, typical OLTP situation. You don't have the high concurrency case. In that case, enable a concurrent execution of single query will help on the performance. So you can refer to documentation on these parameters. It's by default disabled. And next one is we refactored the lookup query, and specifically we optimized the index selection. So in some cases, when you have multiple indexes for certain tags or edges, it now can consider all of your more than one indexes in some cases when it's optimal to do so. And the rest two are not impacting the user spaces, but but it's an optimization. One is the listener interface now support full data acquisition. And next one is the leader table in MetaD is also refactored. I will give some brief introduction of the benchmark side. So basically, comparing with the 2.0, there is no performance regression with our observation. We will not release the whole performance report in this release cycle, but you can still refer to the benchmark between the 1.2 versus the 2.0 here. The last one is the incapability behavior change. As mentioned before, now you have to specify with prop this option to get the properties when you are fetching the subgraph. So this is a kind of incapability because your old query fetching subgraph by default, the same query will not have the properties being fetched. So this is the only major incapability between 2.0 and 2.5. And finally, I would like to give a brief introduction of the whole ecosystem, the surrounding tools. So this is the core part. In this release cycle, together with 2.5 of the core, we have, for our other tools, we still have corresponding releases. For example, like the Exchange, our tooling to support multiple data sources, importing data to Nebula. We have some new data sources introduced. Please refer to the documentation and the GitHub repo. And also one of the features of Exchange, like the SST, is general available to the core in version 2 now in this release. So like the clients, we didn't put the Rust here, but still we have the repo. If you would like to use it, just check out our GitHub repo. And regarding the visualization toolings, previously we only have one tooling named Nebula Studio. And now with this release, we come to the version 3.0. And the other exciting news is that we finally open source this tool. So just feel free to check out GitHub repo, and we come with same license of the core. And another tooling that may be strange to you, but you may already know that, are the Explorer and Dashboard. So Explorer is yet another data explorer tool, which is similar architecture of Studio. It's not yet open source, but it will focus on the area that's targeting to the end user, mostly on the graph expert or data scientist. So we bring a more next level power for the graph explorations on this tour, and I will introduce a bit on that in following slides. The other one is called Nebula Dashboard, and literally it's a dashboard. So it's focusing on the observability, the monitoring function of the Nebula cluster. So previously we already provide exporter, so you can wear it together with the Graph Now Prometheus. But now we have this dashboard to be everything ready out of the box, so you can easily implement a beautiful dashboard with only one package. And the good news is it's also open source, so check out our documentation and GitHub repo. And also on the deployment part, together with this release, we have a major release of our Kubernetes operators. And we also have a repo of Ansible, just lets you know. And another interesting thing is we introduced, we released a new service called Playground. So it's basically a preloaded dataset cluster that without authentication, you can use it with your browser connected, your modern browser connected to internet. You can check it from our documentation and our Nebula website. There is an entry there. So I will give a brief introduction review of the Explorer, the new tooling. You can also play. We have a playground similar to the playground but that's based on Studio. You can play with the Explorer here. So now we introduce some next level abilities for the user to explore the graph now. It looks awesome, right? So the next one is dashboard. You can see we support the machine level metrics and the service level. For example, you can check the meta metrics here. And please check the repository here. It's open source. And finally, we will introduce our new recycle policy. So basically, we will have our cycle will be fixed in 3 months, and every 3 months we will have the code fixed in like March 30th, and 2 weeks later we will have the release. So basically, the release will be at least in the medium level. So we will have the major point, medium point, minor point. And in the minor changes, normally we don't break the capability on the surrounding tool or client level. But when it comes to the media change, you will have to upgrade the clients. And the major level will be a big difference. And in every release of the core part, after 2 weeks, normally we will have the surrounding tool release, but the actual release pace of the surrounding toolings can be different. So maybe you don't necessarily have all the toolings released in together with core, and also you may have more than one releases between the core release cycles. The last one is we come back to the repositories structure. So actually, we are some of you will already know that in the legacy, in the version 1, we are using the mono repository, only a single repo of the Nebula repo, and we break them down into 3 separate sub modules since version 2, and until the 2.5 is keeps so. But in the future release, like the next cycle, the master, we change back to the legacy way. We are using the mono repo now. So we are sorry about the confusing and the inconvenience, but I promise in near future we don't change this for some time. And I think that's all. Thanks. So we will have the QA here or in the end part.
Oh, is there any people having any questions? I think we can have a brief answer here, or we can answer all the questions in the end. So any questions so far? If no, or you can, or we can discuss or chat later after the all the presentations.
Sure.
Okay, thank you, Wei, and great job. And let's welcome the next one, our customer from Akulaku. Let's welcome Mr. Huang.
So hello everyone, can you see my screen?
Yep.
Yeah, okay. And here we start. So hello everyone. So today I'm a ground mining engineer from Akulaku. So today I'm going to talk about how Akulaku use Nebula Graph for intelligent risk control. So first, I will have a brief introduction of what we do. We are an internet finance company and e-commerce company. We are a leading player of internet finance in Southeast Asia. And so basically, this is what we do. Our major product is an installment app. So what is an installment app? For those who don't know much about finance, I will give you a brief introduction. Installment means when you buy something on the internet, if you can't pay the full bill, you can choose to pay part of it, and you can choose to the rest of your bill to be paid by our company, but you have to pay the interest, and we actually make money from the interest, and that is where our benefit from. So for a finance, we are an internet company and at the same time a finance company. For a finance company, there are two types of risks. For our customers, we send out bills once a month, and we will encounter two types of risk and two types of customers. For the first type, they refuse to pay the first bill. And for this kind of risk, we call it fraud, because they refuse to pay the bill on purpose. And the second kind of risk refer to the customers who refuse to pay the last bill, or the third or the fourth, for example, the third or the fourth bill in the whole order. And that kind of risk refer to the credit risk. The major focus of our group is to hunt down the first type of risk, so to hunt down the frauds. And in today's conversation, I will first briefly have an introduction to Graph and the related use cases. And then I will talk about the choice of Graph database in our company. And then I will talk about the Graph processing platform we built on top of the Graph database. And fourth, I will discuss the Nebula use case in Akulaku, our company. And fifth, I will talk about training and deploying Graph models on top of Graph database. What are the basic considerations? And finally, I will give a brief summary of what I talked about today. So first, the introductions about the basic concept and use cases of Graph. So what is a graph? A graph is a combination of vertices and edges to represent relations. So when you want to represent relations, you can think of using the graph as a data structure. And in that way, you can use existing algorithms and solutions, which are designed specially for graphs. And that is the idea. And here is an example we have in one of our data sets. So in general, for the graph use cases, for the first use cases, we use graph for mining. So graph mining is a special case of data mining. And there is something special about graph is that graph is particularly useful for visualization. So visualization is a very important part in our everyday usage. The second use case is that we can use graph queries to implement complex queries. For some problems, although in the first place, they may not seem to be related to graph, we can still translate these problems into graph settings and implement the queries in graph queries. In that way, it may help us to understand the problem and to maintain the program. So for the choice of graph database, actually we have tried quite a lot, and we have actually tried 3 different graph database. Each of them failed for one or more reasons, And actually, the reason they fail actually highlight the key considerations when we are choosing graph database. So the first consideration is scalability. And the first database to be ruled out of the game is Neo4j, because for the community version, it only supports single node deployment. And the second consideration is data import, which means when we import the graph data for the first time, the time of importing the data must be low. And the counter example here is dgraph. So we tested dgraph. Dgraph is actually a very interesting graph database. It's implemented in Go language. It has very cool academic idea. It has several papers published, but the implementation sucks. Especially the data import tool. So when we test the database, we can't even start our test because our graph data is so large that the data import program for dgraph fails. It never finish. Not even slow, it never finish. And the third consideration is, of course, efficiency, query efficiency. And that is, it also highlights the reason why we choose graph database, because graph database are optimized for certain types of queries. And the counter example here is Genus Graph. So we tested Genus Graph. The reason why we choose it is that it is kind of appealing to us because it has big data backends. The backend can either be HBase or Cassandra. That give us the impressions that, well, Genus Graph might be able to hold the huge graph data set we have. And actually it did. It was able to hold the data set, but that is all it could do. It can hold the data set, but you can't query it because the query, even the queries are so slow, even a 2-hop or 3-hop query. And that is a nightmare. And because of that, after some experiments, we all three database fail, and we come to the Nebula Graph. And actually, because of what we have suffered before in all those databases, we decided to have a complete test on Nebula Graph. We don't have too much trust then. This is our graph size. It has 1 billion nodes and 10 billion edges. And the queries they don't look very difficult. They have, we perform our queries in batches. Each batch has 3 types of queries. It has one 1-hop query, 2 2-hop query, and 1 3-hop query. That actually match our actual design of graph queries in our in production in our company. And we randomly pick 5 million nodes to start our query from, and we vary the number of machines in the clusters. This is the diagram we get after the experiment. We can see that the throughput of the Nebula Graph is actually quite nice. It reached the maximum throughput when we have 12 machines and at a concurrency of roughly 100. We can reach a QPS of 5,000, which means 5,000 batches of query per second, which is, well, quite nice and satisfied our needs. So we decided to, well, maybe we give a try to this graph database. And early this year, we have a new version. Well, Nebula had a new version 2.01, and we decided to give it a try. But unfortunately, we observed some problems when we were using version 2.01. The first problem is leader change. We observed frequent leader change exceptions. When we were trying to import our dataset. Actually, leader change does not crash your program, but you need to retry. it's fine when you are when you are importing data if you retry, but if you are running a query in production, that is catastrophic, and we were not sure whether leader change exception will appear when we are performing graph queries. So we decided that, wow, that was a big problem. And the second problem is the high CPU workloads, because in some use cases, we have huge subgraphs in queries. And because of the two reasons, we decided to downgrade to version 1.0. And early July, I guess, yes, we have version 2.5. And we decided, once we have the new version, we decided to have the same test before we actually start using it. And we basically have the same setting, but now we don't have time to vary the number of machines. So we choose one setting. We build a cluster with 7 nodes, each with 256 gigabytes of memory and 32 cores. And we have the same graph as before, 1 billion nodes and 10 billion edges, and the same experiment setup. And this diagram shows what we have. So now I'm going to talk about the architecture of our graph platform. So only a single graph database is not enough for satisfying our needs. So we build a platform on top of that. And there is another point I want to highlight. To satisfy our need in using graph processing and graph computations, actually graph database is not the only option. For some use cases, graph database is particularly suitable, but for other cases, it's not. Graph database are especially suitable for cases when you want to extract a local subgraph. So example applications includes ad hoc features, deployment of graph neural networks, and label propagations. But there are also some other cases where still you need to use graph algorithms and graph implementations, but you don't need to use a graph database. For example, for the real-time community detections and anomaly detections, for these application scenarios, we design our own graph computation engine. And here is the architecture view of the whole platform. We have the applications which I described just now, and we have platforms to support different kinds of applications. To support the availability of platform, we have different infrastructures. So graph database, and we also need the help of different big data clusters like Spark, like Hive, like Flink, and HBase. Okay, so let's zoom in and see what is happening in the graph database platform. Basically, we need to build several data utils around the graph database, and we do need to consider several issues when we are setting up our graph database and graph database clusters. So basically, we have 2 different modes of deploying the database. The first mode is that we have a cluster, and we have 2 clusters. Each cluster have 2 different Nebula instances, and we set the replication num to be 3. And in this case, you have 2 clusters for high availability. And when you update the graph, you write to both of these clusters to ensure consistency. And this setting is to support the graph features deployment in production, where high availability is very crucial in the case. And there is also a second mode, the AP mode you can see in the graph storage layer, which means we have individual graph database instances. This is mostly for testing purpose. So when you are training and testing your graph models, you set up individual Nebula instances in probably isolated physical machines. And this is to minimize your influence. to production environments. So as a whole, we are actually ensuring the high availability of the production clusters, which you see on the left. And to ensure the data consistency and for the convenience of initializing the data, we need the data production layer. As you see on the third layer, we need support from Hive for batch mode, batch import. So we digest data from Hive and write it to Nebula using Spark. And for real-time import, we have Flink clusters deployed. We have new edges coming in Kafka in real time. And we also have supporting platforms like service monitoring, data monitoring, sandbox, clustering, scaling, and scheduling. So now we come to the concrete use cases in anti-fraud in our company. So here is an example of using Graph Studio to perform graph exploration and visualization. And so in general, in our company, there are 3 different use cases. The first use case is deep relation mining and visualization in fraud case investigation. So when you detect a suspicious group of fraud, you need to figure out what is actually happening. And Graph is a tool that is particularly suitable for this case. And the second use case is the calculation of device ID. We need to consider the connection of features. And lastly, I'll talk about deploying graph models on top of graph database, like label propagations, etc. So the first case is deep relation mining and visualizations. We have some features deployed on top of graph database, like, for example, please, for a certain user, please tell me the dangerous users or suspicious phone numbers which are 3 steps or 2 steps away. So these kind of features. And we also have visualizations with the help of Graph Studio. The second case is the calculations of device ID. This is the case, this is a very good example of, in the first place, it might not be related to Graph, but when you translate it to Graph and Graph models, they actually make it easier to maintain and to understand. So in our case, when we are determining the ID of device, we need to consider the surrounding features, the features that are related to the devices. And the problem here is that different devices may share different features. And when we are translating our rules of determining device ID, we come to the conclusion that, well, maybe modeling features and devices as node in a graph will make it easier to maintain. And that's what we did. We modeled what we are going to do in the graph. You see here, we model device and related features as nodes. And we implement our rules of determining device IDs as graph queries. In that way, it makes it easier to understand and maintain. But there is a major problem here. We need to ensure consistency when we are doing update, the device ID update in parallel. And to do so, we introduce logs. So logs, when we are calculating a certain part, calculating a device ID based on a certain part of the graph, we log part of the related part of the graph, so that other requests will not be able to access this part of the subgraph. So as I said before, not all use cases in graph need graph database. And what are the graph models that are particularly suitable for graph database? It is the models that based on subgraph extractions. So we start from a node in the center and we extract a subgraph center at a node. It includes the first type of models includes no related subgraph features. For example, the suspicious nodes, which are 3 steps or 2 steps away. And second is label propagations. So you have some labels, for example, risk labels or good labels, and we attach those labels to the nodes, and we propagate those labels according to some rules. And lastly, and most importantly, the graph neural networks. To deploy graph neural networks in real time or nearly real time, we do need graph database. And all these models rely on subgraph extractions used on graph database. And the difficult part here is that the deployment usually require high reliability of the database, and the execution time must be very small. A typical example here is the Graph Sage model. And here is the picture of the model. So in general, there are three considerations we have to pay attention to when we are training and deploying the models in production. First is the execution time requirement of the concrete scenario. Is the requirement strict or not so strict? Second is the size of subgraph we extract. Are the subgraphs, could the subgraph be exceptionally large, or are we allowed to take some kind of sampling in the process? And third, we need to compare two different updates. First is the change of the graph, and second is the calling of the model. So the number of business calls from the particular scenario. And we need to decide which is larger in our particular use case. The first example is subgraph extraction during application. So here, by writing application, we mean that the customers are coming to our company applying for quota limit, which means to apply for the amount of money they can borrow from our company. And in this scenario, we need to calculate the subgraph features, and the execution time requirement is actually not very strict. As long as you can finish the whole process in 1 minute is fine. And second, the size of the subgraph could be large because sampling is not allowed when we are running the model. And third, the change of graph, which means the deletions and additions of edges in a graph, the number of deletions and additions are significantly larger than the number of calls of models. So we decided that we deploy the model, we run the model whenever there is a call from the front end, and we choose to calculate the feature when the model is called. In this case, we need to pay attention to the reliability of graph database. Because of that, we introduced the two cluster settings I explained before. The second case is the label propagation when we are placing order. So by placing order, we mean that it actually means when a customer places an order, we can still determine whether or not we approve the request, and we can turn down the suspicious request. In this case, we need to obtain the label propagation score, and the execution time limit in this scenario is very strict because there is a huge number of orders each day. And also the size of graph could be large because sampling is not allowed. And also for the third factor, the change of the graph is smaller than the calling of the model. So the change of graph here means the addition and deletion of edges. And the calling of model is actually equivalent to the number of orders each day. So you can see that there's a huge difference. So in this case, we decide to calculate the model score, not when the user placed the order, but when the graph is changed. And we actually separate the calculation of the model and and the access of the score. So when you calculate the score, we write it to the database, and we read the score online. We read it from this database, the same database instance. And the database instance serves as a barrier to separate online calls and our real-time computation of label propagations. And the third case is a similar case, that is the graph neural network, but we have a more difficult situations because the execution time of graph neural network models is usually significantly higher than label propagation, and it's also more complex. And also we have the same requirements for the business from our business side. We have very strict limit of execution time within 200 milliseconds with 200 milliseconds, and the size of graph could be large because sampling is still not allowed. And we also have the same problem, the same configuration. The change of the graph is significantly lower than the number of orders, I should say the number of orders of the model. So still, we choose the same solution. We separate the calculations of the model and the online calling from the other systems. In this way, we ensure that if there is any delay in the calculation, we will not influence the overall decision process in production. And that delay could be catastrophic. And also we have different some other options. For example, we can use sampling when we are extracting a subgraph, but that should be approved by the business guy, because we produce model to our anti-fraud strategy friends, and they have to decide whether they are going to use our models or not. So lastly, finally, I will give a brief summary. So what's cool about Nebula? The first and the most important part, the issue is that it's super fast in data import, which is much faster than all the other graph database we tested. And secondly, the second appealing part of the of Nebula is that it can offer high availability for huge data set. And next, we plan to improve our graph platform on top of Nebula and make it easier to train and deploy graph models. And we will continuously provide feedback to the Nebula communities. So this ends my talk today. No, or we wait for the QA part?
I think let's wait for the QA part.
Okay, okay.
And thank you very much for sharing everything.
Okay, so I stopped sharing my screen now?
Yes.
Cool.
Yes. Thank you. And now let's welcome the Zhichao from Facebook to share their experience of supporting social graph.
Okay, so can you see my slides clearly, and can you hear me now?
Yes.
Okay, so thanks for the meetup invitation. I'm Zhichao from Facebook, and I'm working on the RocksDB team. So we know that Nebula uses RocksDB as its basic storage engine. So after we listen to the two presentations about the graph store itself and how the users use it, and now we can dive in and look at its storage engine, RocksDB. And here is today's agenda. So first, I will talk about how we collect, analyze, and model the workload of RocksDB at Facebook, and it has been presented as a paper last year. And then I'll talk about the current trends that we separate the storage and the compute clusters, achieve the disaggregation, and how RocksDB is customized and improved for those new architecture. So let's look at the workload part. Maybe I can just use several minutes to introduce about RocksDB. So we know that Nebula uses RocksDB as its storage engine, and all the graph vertices and the edges are stored as a key value pairs inside the RocksDB. And the RocksDB is LSM tree-based key value store. And when we do the insertion, all the new key value pairs and deletions are cached in the mem table, so those parts. And after the mem table is full, the key value pairs are sorted and flushed out as the immutable SST files. And they are managed in different levels. So from level to level, the key ranges might overlap with each other, but in the same level, there's no overlapping. So new SST files will be merged with the old SST files in the next level by compaction. And RocksDB supports a very simple key value interface like get, put, delete, iterator, merge, and other more advanced interface like delete range or single delete. And RocksDB is an embedded storage engine, and it is widely used at Facebook and in other big companies. So now I will introduce 3 major use cases at Facebook, how we use RocksDB to support social graph and other data stores. So the first use case is UDB. It is actually a very large, maybe the largest MySQL database. So we replace the embedded InnoDB, original InnoDB, with RocksDB as its search engine. And it will provide us pretty good space efficiency and pretty good write performance. So we have a layer called MyRocks, which converts the SQL data or the SQL query to RocksDB. And here is some of the examples how we do this conversion. So usually we use MySQL table index number as the prefix of the key, and then we use the primary key, for example, the vertices number, and also the other key as the portion of the RocksDB key, and stores other information as a value part. And for the social graph, we know Facebook maintains the world's largest social graph, and we do the graph partition. You can seek to the papers about this partition. And each graph partition will be stored in one MySQL table. So there'll be some interesting localities. And furthermore, we call the vertices as objects and the edges as associations. So we use different column families at RocksDB to store the objects, associations, and the secondary association indexes. The second use case is ZPDB. So ZP is a distributed key value store based on Paxos. So ZP will maintain thousands of the RocksDB instances. And for example, one host will have about several hundred of the RocksDB instances. And we have the primary one, which will provide the strong consistency. And the secondary one will be synced after that. It is pretty simple. There's no translation layer. So all the application user key will be the RocksDB key, and they will do the get, puts, and also other operations. And we have a very complex sharding mechanism to distribute the keys and key value pairs to different RocksDB instances. The third use case is a pretty interesting one. So we call that UB2X. It is also a special distributed key value store, which uses RocksDB as the storage engine. And this key value store is used only by the training and inferencing platform of the AI ML services. So we store the user features in this platform and provide the read and operatings from different AI ML services. So from now, we know that RocksDB is used everywhere, including Nebula's usage, but actually it's hard to understand what is happening inside RocksDB, what's the workload, and how we can improve the performance based on the workload. So we introduce a set of methodology and tools to address this issue. So first, we have RocksDB, and we have different applications running on top of RocksDB. And then usually we just run the DBbench or other benchmarks and compare the results with the scenario we want to use RocksDB. And then we can tune or improve it. But without the real world workloads, actually it is pretty hard to get a very accurate benchmarking. So what we did is we introduced a tracing framework for RocksDB. We are able to collect the trees, and then we have analyzer to generate a set of reports from the tracing files. And based on those characteristics and analysis, we can use different mathematical and statistics models to get the profile of the workload. And finally, we can use those models to rebuild the new benchmark. So now we have a closed loop of this process. We can continue to improve the benchmark and do better benchmarking. Moreover, we can replace the trace, which can be nearly the same as a real world workload. And then we can refine the model and then improve the benchmark. So now I will introduce some of the results we collected from Facebook, the social graph, and other use cases. And for more information, you can seek to our papers. So the first question we want to answer is, what's the query compositions and what's the ratio of them? So we analyze them and get the following results. Actually, for the UDB, which is for the social graph, and ZPDB, they have a lot of get or point lookup queries, more than 70%. But for the UP2X, merge is heavily used because for the UP2X, which is like user features, they have a lot of updates. When we update a keyword pair, usually we just do a get and then update it, do a put. But it will waste a lot of time when we do the read. So merge is just a single put, special put. We just store the delta portion. And when we do the get in the future, we just combine all the merge information and get the final results. And for the one-for-one RocksDB instance, we could have different column families. And you can see, even inside the same DB, different column families can have different query compositions. For example, in the UDB use case, object is the vertices we know, or vertex in the social graph. And we do a lot of point lookup, and some of the iterators, we scan this graph. For example, how can we know someone is connected with you? We need to do a scan. Also, for the association and some of the unrelated data of the social graph, they have a lot of point lookup. But for the association secondary index, they do a lot of iterator, because sometimes if we do a graph search or do some data mining or the AI service on top of the graph data, we need a lot of scan and a lot of iterate for directions we want. So it has a lot of iterator and have a lot of single delete. The second thing we want to know about is the key and value size distribution. So it influences the performance of the RocksDB, and also we could know whether we need to do the key value separation, we want to do the improvement for the compaction and flush, and we may be able to improve the caching in the memory. So usually for the key size, it is relatively small. Usually that's smaller than the, 50 bytes. And the key size does not change much from case to case. But for the value part, they have a very big standard deviation, which means the value changes a lot and it will have a long tail distribution. When we look at the CDF, we plot out for 3 use cases. You can see that actually in the UDB case, its key size has a very long tail distribution because maybe someone just have a long ID to represent the graph. But you can say in the ZPDB case, since it is a distributed key store, we generate the key based on the rules we have internally. So its size just have some fixed number, and we don't see any distribution here. So it is similar in the UP2X, maybe just like integer as a key or some of the 20 bytes hash value as a key. But for the UDB, it has a long tail distribution. Value size is also pretty interesting. Value size distribution is wider than the key size distribution, and also it is closely related to the data type stored in this use case. For the UDB, the size can be hundreds kilobyte size or megabyte size level because maybe someone wants to store very long post, or if that is a small photo, we may store directly in the graph. But if it is very large, we just store it as a metadata and put the videos and also put the photos in other storage and just store the metadata here. So we can see the long tail distribution, but also some fixed size length of the value. For the UP2X case, since we use it to store the user feature or user profile, and usually we have some fixed size structures to index them. So we can see this kind of jump in the CDF. Another pretty interesting things we want to know about from workload is the locality of the key value pairs, right? What's the distribution of the hard key value pairs and what's the cold key value pairs and what's the correlation between them in the key space. What we did is first, we dump out all the key value pairs from the DB instance and then sort them as that's the same order as they are in the DB. Then plot out how many times they are accessed throughout the, for example, 24 hours tracing. Then we can see those distribution heat map. In the UDB case, remember that that's a MySQL storage. So we use a red line to separate the different MySQL tables. And we can see some strong key space locality, which means hot key value pairs are usually stay together. You can see those green lines, green blocks, and the cold key value pairs are located together. So those are the very cold region. This is a hot region. So that's roughly what we find out from the locality. And it shows up in all of the use case at Facebook, and which trigger us to improve the caching efficiency such that the read performance can be further improved. And we have more information about the workloads, but due to the time constraint, I just give them. You can refer to the paper and find out more details. So the next part is about the monitoring, how we do the tracing. Actually, when we use RocksDB, since it is just a library, we will have an application process which maintains the DB pointers and call those DB APIs. If we want to control or access a certain DB, the application need to expose some of the API to the upper layer such that we can access the DB. But it is also possible that we can have a separate threads running inside the application as a Swift server. So this monitor can access all the DBs registered in this application. Then when we open a new DB at this host, this one will be automatically registered at the monitor. And when we close the DB, it will be removed. So we can just use some simple Swift API to communicate with the monitor and achieve any operation we want for a certain DB. So here are some use cases. As I mentioned, although we have the tracing module, but we cannot control that when the DB is running. So by adding those monitor module, we just use a command line to communicate with the Swift server, and then we trigger the tracing start and then end the tracing. Also, we can manually trigger the flash compaction and also do some adjustment for the DB or even change the mutable options. Also, we can use this one as an interface to monitor the DB status and also customize the logging and the statistical mechanism. Finally, we usually use these things to do the debug because we can access any DB we want and then dump out some of the content, look at some of the SSD files. It is pretty convenient. So this is the module we use to do the tracing and also to adjust the tracing options. So for the second portion, that's about the current and the future of the RocksDB in terms of the storage or the infra part. So that is what we change for the disaggregated infrastructure. Why we need to disaggregate the storage? So first, in the traditional setup, we just run RocksDB in a server which has like 4 terabyte or 10 terabyte SSD. And then we do the compaction in the server, and the applications just issue the requeries to the RocksDB instance in this server. But it has a lot of limitations. For example, we cannot increase the DB size larger than the SSD capacity in this server, and we have imbalance of the CPU, memory, and storage usage. So by separate the storage with the computing power, we could achieve better flexibility and improve the elasticity in the system. So we have a shared storage pool, and we just store any data there and access data throughout from the remote storage. So that will provide a lot of flexibilities for the RocksDB. It is kind of similar to the remote SAN we have in the past, but it's more flexible. It is kind of similar to the Snowflake's data lake concept. And we can reduce TCO of the system, and also we could achieve better orchestration, management, and better resources scheduling. So here is a long-term goal. We have shared storage, which maintains thousands of the SSDs, HDD, or even tape. That's a very complex storage pool. And then RocksDB primary instance will store the data at the remote storage. And we can have hundreds or have tens of the RocksDB read-only instance to access the same data. So we can respond the user throughout the read-only instance. That's one point. Another point is, in the past, when we want to do the analyzing of data of this RocksDB instance, we need to do a scan and dump out all the data, something similar like ETL in the data warehouse. But now we could let those offline jobs directly reference to the SSD files in the shared store lake, and then they will just do the job by themselves. That's read only. So each other does not have the influence and impact. And we can do the background compaction, which will not use the primary instance CPU, memory, and network bandwidth. However, we have a lot of issues when we do such kind of disaggregation. Since we need to access all the data through the network, we will have high average latency, and also the tail latency is really low, and it's hard to predict. And we can potentially have different kind of failures from network side, from storage side, and also we have a complex software stack to do the troubleshooting. So the first improvement we are doing is to introduce a local cache or the secondary cache. So when we offload the storage part to remote, actually for the local flash, it is not efficiently used. We use them as a persistent cache. And for each DB instance, its data will be cached in the memory DRAM block cache first, and then they'll be stored in the local flash cache. So that will improve a lot of performance because majority of the data workloads have a very strong locality. So when those hot data are cached at the local, the read performance will be improved in a very clear way. The second improvement we want to do is remote compaction. So the basic concept is the primary or the RocksDB instance just issues the compaction command and what the files to be compacted. Then at the remote site, close to the storage, the compaction worker will just gather the information and do the compaction. Since all the SSD files are immutable, so it will not influence the primary RocksDB instance performance. After the compaction is done, the result will be returned to the primary and updates the manifest and other metadata. So this is a kind of the communication between the primary and the compaction worker. The last piece is about the error handling. As I mentioned, different from the previous use case, we have the local and it is pretty reliable. Now we need to go through the network. So we need to define different error types. For example, some of them can be retried, some of them just file corruption, some of them might be the system corruption. So we identify different error types and have a different fine-grained reactions to the errors. And then we will recover them at the RocksDB parts. For example, redo the flush, redo the compaction. And during this process, RocksDB is not suspended. It can still accept the read and the write query. So that's like a best effort recovery for the RocksDB. And maybe user will not be aware of those internal automatic recovery. Okay, that's almost the content I will present. And finally, that's about the RocksDB. We want it to be a fast and easy to use persistent kilo store for any workloads on any hardware platform. And here's the GitHub, and welcome to use it and contribute to the community. Thank you all, and welcome for the questions.
Thank you, Zhichao. I think we can have the QA session at the end after this. So let me first share the screen. Okay, can you guys see my screen?
Yes.
Yeah, perfect. Okay, before we go to the QA session, so first, so this is our Slack channel. And if you guys have any questions, please share and do not hesitate to shoot any questions that you may have to our Slack channel, and we will help you there. And here is also our GitHub website and Twitter, our official website, and our Facebook, and also our forum. All right. Let's talk about if you people have any questions, we can answer here. So first I have a question. So Wei, can you share some roadmap that we may include in the next version?
Hello. Actually, yeah, we are not sharing roadmap long before, but if you go to the GitHub, you can see many PRs was tagged as a sort of projects, and you can check the project. There are some backlog and to do and progress of what features we are working on. And I will weekly or bi-weekly share our highlights of what's being done on the master head, but we are having a next cycle in near future in a couple of weeks, which is 2.6.0, but the release content is not finalized. So, but when you're referring a roadmap, for now it's only can be carried from the project. But if you have some, I mean, our community users have any concerns or questions regarding the roadmap, it's more than welcome to be queried in issues or Slack or in the forum. Yeah.
All right, thank you.
Yeah, thank you.
Yeah. Any other questions? And Zhichao, are you online? If you are there, can you share more information about how the RocksDB is like debugged in Facebook?
So actually, we have several ways to do the debug. First, we have two really powerful tools. One called LDB, and another called SST-dump. So LDB is like a tool to get general information of a certain DB instance. It will get information from the manifest. We'll just assume that you have non-corrupted SST file manifest. And also for the SST-dump is like when we have the corrupted SST file or got some data corruption, we use that one to get the detailed information of the certain SST file. So that for the DB instance debugging. And also we look at the log. The log is really powerful and detailed. So we can look at the log and get all information about operations. So we log all the important things happens inside RocksDB in the log. And for the other part, as I mentioned, we have really complex and useful monitoring system. So for each DB instance, when it is opened, we all know it is online and it will report the DB status to us. And we are able to, if we need, we are able to control this DB instance to do some manual compression, to do some rearrangement, or do some backup things. So that's like the part easy to use. The other part to make the DB easy to use. Otherwise, I know that the application need to provide the rewrite API from RocksDB layer to your layer, and then higher level application or the people can call those API. But by using that monitor parts, we can just write a Swift command line, and then that will just connect to the DB and look at it.
I see. Hope that we can utilize the feature provided by RocksDB and beef up our product. Thank you very much.
Yeah, thank you.
All right. Any more questions? If no, or if you have any questions in the future, you are welcome to ask anything in our Slack channel. So let's call it a day. And thank you everyone for attending our meetup. Thank you.
Thank you. Have a good night.
Thank you.
Thank you.
Bye.
Bye.
Bye.